I'll start off, I'm just going to go through a bit of an introduction for SOS and SOS Multistripe. Some of this might be familiar to some of you, that's okay. And then later on, we'll be going through APT and ETC specifically as well, so you can kind of see how this all meshes into the proposal tools you have available to you for Cycle 5. So broad recap, NIRISS is one of the JWST instruments, and we have this mode called Single Object Slitless Spectroscopy, or SOS. And this it all hinges on this one optical component we have, this GR700XT grism, which disperses the light for a given target from 0.6 to 2.8 microns in these three kind of distinct cross-dispersed spectral orders. Now, typically this mode is primarily used for transiting exoplanet science. This is the vast science cases that people approach with this mode. And you can see a bunch of results here. We have like ERS observations of WASP-39b, some exciting results for TRAPPIST-1c and WASP-17b in emission or transmission. So really that's the bulk workhorse, but not necessarily the only thing you can do with SOS. It is just at its core like a spectrograph. So if you're interested in spectra from 0.6 to 2.8 microns, maybe SOS will be useful for you. So before I start talking about multistripe, I just want to give you some key components so you can kind of frame your thinking about SOS data in general and maybe some idiosyncrasies of it. So first off is, you might have noticed this, it has this very like typical overlapping traces. I think this is the only really mode where you have overlapping traces like this. So you have order 1 and order 2 like physically occupying the same space on the detector, at least partially. Now this can complicate the spectral extraction a little bit, right? Because you can't just do a simple box extraction or optimal extraction. You have to do some disentangling of the two different signals to make sure you're not contaminating your spectra and get really accurate results. Now, people have different ways of handling this, but in the JWST pipeline, we have this nice algorithm developed by the University of Montreal group called a TOCA. And that kind of builds like a linear model for each pixel to kind of figure out if we have one wavelength over here and one wavelength over there, how do we weight everything appropriately to get the correct extracted counts for order 1 and order 2. The other really key important thing about SOS is that it's a slitless spectrograph, right? So it's not like a typical slit like you might be familiar with for NIRSpec bots, right, where you're just getting one trace. The whole field of view really is liable to contamination from other sources. So this is a kind of schematic of this. Sorry for the slightly low quality. I want you to focus on the black star. This is where we would actually place a target on the detector for its orders to be dispersed by that grism in the nominal like substrip 256 subarray. And you get the order 1, order 2, and order 3. But if we have other sources in the scene, depending on where they are, they're also going to disperse light into the field. And really that depends on whether they fall on this pick-off mirror, which we have in here blue relative to the kind of detector space. So something in green, for example, if you had a bright contaminant here, it would actually start dispersing this like order 0 right through the traces. And you might be interested in getting science there. So you do need to be a little bit cautious about this contamination. And we have a contamination tool to deal with this on ExoCTK, which you can definitely check out. But really, wherever the contamination is, you just need to be careful it's not bumping into your traces. Now, the other part of this is that you get a lot of order 0 contaminants, right? So if I flip back a second, you might have your direct image down here. You might have a bunch of these little order 0s. And the way the detector is kind of structured is that you can only have them rightwards of like column 700. So you can imagine this green star here gives an order 0 here. If the green star then falls off the detector, it's like physically impossible to disperse on the left half. And that's kind of what you see here in most observations, right, is they have some level of like order 0 contaminants. So here's some example here with the order 3, 2, and 1 traces. Just contaminating space, and you just need to be a little bit careful, but obviously they don't contaminate this left-hand side. A nice way to pick these out if you want to is you can prep immediately following your observation an F277W observation, and that just applies a filter to the grism instead of just the clear throughput, which chops off all of the orders below just chops them off to be in this filter, this 277W. So really only what you get there is the tail end of order 1, and you can pull out all of your order 0s very clearly and understand where your contamination is. The final subtlety about being a slitless spectrograph is that we have this very interesting uniform structured background. And the way to imagine this, again, if I flip back a few slides, we have different orders being dispersed on different areas of the detector, and really their positions are dictated by where the stars end up falling in the pickoff mirror. So we can't get order 1 here further to the right than a given position. We can't have order -1 further than a given position because stars start to fall off the pickoff mirror. And that produces this very interesting structured background. You can imagine the background is nominally like a uniform illumination across that pickoff mirror, but each order that gets dispersed is going to have a different shape on the detector. So you can see that kind of here in these order -1, 0, 1, 2, and 3. And then when you combine them together, you get this really characteristic SOS background structure. We have this like broad black background here with a sharp jump around column 700. That's where this order 0 break happens, and then slightly trails off towards the longer columns. We know this background changes with sky pointing in time, and we just actually in the recent pipeline update will be including like a background correction in the pipeline by default for SOS that uses empirical observations to kind of weight the background and appropriately subtract it. Okay, so that's some sort of key features just to get you grounded, and now I'll start digging into the subarrays a bit. So really at the moment there are only 2, well, 3 technically if you include like full frame readout, but 2 standard sub-SOS arrays. And that's substrip 256, which is the kind of workhorse. This gives you full coverage of all 3 traces, but saturates at this J magnitude of around 8.4. And then we have this other subarray, substrip 96, which is like a small, thinner region. We shifted up a little bit and cut off most of the pixels. And really, you lose the short wavelength order 2 coverage below 1 micron. This is this like nice tail here. And you get saturation is improved a little bit. You only get there at J magnitude of roughly 7.4. So this is great because it gives us some flexibility, but there's some issues to it as well, and kind of prompted the investigation of multistripe, is that 25% of transiting planets have a J magnitude less than 8.4. So we really wanted to give that capability and kind of broaden the use case of SOS, and that's kind of where these multistripe subarrays are going to come in. So these cover the same detector footprint as substrip 256, so you're getting exactly the same wavelength coverage, but it operates in stripes, so it reads stripes of the detector at any given time. And what that means is we can dramatically improve the bright limit. So for the smallest stripe size subarray that we've defined, you can reach like a J magnitude of 3.5 without any saturation at all. And importantly, now pretty much every transiting host star can now be observed with SOS. So if you can think of a planet that transits, you should be able to observe it with JWST now. So just a quick point on heritage. So some of you might remember the NIRCam DHS that was advertised for last cycle observations. This is really like a kind of follow-on from that, and we're leveraging the successes of that and the understanding of how this works to kind of implement it in slightly different way. So in multistripe, we had this, multistripe for NIRCam DHS, we had this situation where we had lots of spectra being dispersed across 4 different detectors. We were worried a bit about bright limits and data volume limits, so we wanted like an efficient way to jump around the detector and read each spectrum one by one rather than reading out the full detector. And really that's what we're doing here with SOS Multistripe as well. It's instead of jumping around the detector, we're just jumping along it and reading every piece of the subarray we're interested in just a bit at a time. So you can see JWebbinar 35 if you are interested in NIRCam DHS. And I just wanted to quickly highlight that the DHS implementation is ongoing. If you have questions about it, you can reach out to the NIRCam team through the JWST help desk. Okay, so next we can jump back to SOS. So SOS nominally has all of its subarrays operating in one single channel of the NIRISS detector. And the way it works is you just read along this fast direction first and then the slow direction second. So we're reading column by column, just quickly along here till we reach the end of the detector, and then we jump back to the front. And that defines like an integration. Okay. Multistripe is a little different. It's kind of a different paradigm, so you won't be too familiar with it. We're now splitting the regular substrip 256 subarray into stripes, hence the kind of multi-stripe. And the subarray name that you'll use encodes the stripe size. So here's an example here for sub 680 stripe SOS. And in that case, we have the first stripe, which we call integration 1A. We'll read out and we'll take all of our groups up the ramp. We'll be reading out until we finish the integration. Then we'll hop over to the next chunk in the nominal subarray and read out the next integration, do the integration. And then we'll move on to the third one and complete the full image, so to speak, but we put it into 3 different integrations. And that's the concept of the entire SOS multistripe, is that you just change your stripe size and you're just reading out a portion of the detector at any given time. That's really where the advantage of bright limit comes from, right? If you're reading out less of the detector at any given time, you can read it more quickly. And if you can read it more quickly, that means you can observe brighter targets. So one subtlety is that to improve the just general sensitivity and noise on the multi-stripe subarrays is that we interleave reference pixels. So this is another option with multi-stripe, is that before we hop to the next integration in our image that we want to cover, we can jump back to some initial reference pixels and read them out again to make sure that we get a nice correction. And what this means is that actually, even though I show you this kind of nice representation here in the top, the actual early stage data products for SOS multistripe are going to be quite different to what you might expect. So that's kind of what you're seeing in the bottom here in this not to scale timeline. So we've read out the left reference pixels, we read out integration 1A, and we go back to integrate the left reference pixels, do integration 1B, and so on for 1C, and then we start this pattern over. And this is what the time series is actually going to look like, right? You're not going to get in the uncal file these normal subarrays that you'll be looking at. You'll be getting these smaller chunks of the subarray all stacked together. Now, that doesn't mean that you're going to have to completely change your reduction pipelines, because the hope and the target right now is that around the reference pixel correction step is that we can start to stitch all of this back together. We can do a bit of quilting and stitch all the integrations together so that we put them back in that nominal substrip 256 subarray format. The only real caveat being is that we never actually read the right reference pixels. We only read the left ones, so we might have some like dummy values or NaN values just to pad those out. But hopefully this gives you an idea of what the kind of timeline structure of this is. So for transit science, this is kind of important, right? Because you're probably used to being in a kind of paradigm where you're reading out the whole detector group by group, and that, for a given integration, you roughly have the same kind of timestamp for every wavelength. We're not doing that with multistripe, right? We're reading a portion of the detector at any given time. So each multistripe stripe is going to have slightly different timestamps. So I've kind of tried to indicate this here. This is purely like illustrative. It's not like actual signal to noise or anything. But, we're going to read stripe A, then read stripe B, then read stripe C, and then we're hopping back again. So we're going to have these slightly different timestamps along our light curve for each of the different slices. And that will be obviously wavelength dependent, right? Because we're reading out a spectrum. These will be recorded by the pipeline and included in the uncal files, but we're still developing the actual mechanisms behind that. So the idea right now is that hopefully we can keep these like raw timestamps all the way in through the later data products, but there might be some small collapsing that might be necessary just to get the pipeline working and white light curves extracted. But just important to keep in mind when you're fitting light curves and comparing light curves. Okay, so as I mentioned earlier, SOS multistripe is improving the bright limits. So I just want to explain this a little bit more. We're reading out a smaller chunk of the detector. We take less time to do it, and our effective exposure time gets reduced so we can observe these brighter targets without saturating. That sounds great, but there is a trade-off, and that trade-off is signal to noise. Okay, so For a given target, your signal to noise is going to scale proportionally to the square root of 1 over the number of stripes. And the way you can conceptualize that is, right, when we're reading out integration 1A here, we're not reading out any of the rest of the detector. For a normal subarray readout, we'd be reading out the whole detector at once, so we're always getting counts from these in these other regions. In this, it's basically equivalent to cutting your exposure time by 3, right? Because you're not going to read it out, so you're only going to have to do one chunk and one chunk and one chunk. So you really want to keep this in mind for your observations, and I'm going to go through a bit of steps to help you understand this. So we're going to be building off this plot for a while, so I want to take time to describe it. I want you to consider in your mind the relative signal to noise between a source at the subscript 256 bright limit, so that's the right-hand side of this plot, 8.4 JMAG, and a source at the bright limit of a stripe of size n. So you can imagine these stripes. We only have 4 subarrays, but you can imagine them of any given size. And you'll see that you get this characteristic curve as a function of the size of stripe that gives you this relative signal to noise. And there's some trade-off here, right? If as you move to bright targets, then you increase your signal to noise because you're getting more photons. But you start losing signal to noise because you have this lower effective exposure time, and your readout inefficiencies become a little bit more dominant over your actual science exposure time. So you get this characteristic curve. Now, for the 4 subarrays we've picked here, the 17, the 60, the 204, and the 680, it's not too bad. Okay, we get the optimal kind of signal to noise, relative signal to noise is only about 85%. So you're taking like a 15% hit relative something at the bright limit. And really, if you're using some of these broader stripes, it's not a big hit at all. You're talking about maybe 3% or so. Now, the big caveat is that this is for like an optimal example. And in reality, we can't provide every single stripe of multi-stripe. There's a limitation, not just in terms of technical effort required, to commission all of these subarrays, but also in terms of like detector restrictions on what size we can make the subarrays. So these are the 4 configurations we have available for cycle 5, along with these dashed lines. And you'll see that this signal to noise curve changes when you have distinct stripe sizes instead of relative stripe sizes. And the reason that is because you can imagine if you're at like subscript 256 and you immediately drop down to a stripe size of 680, you're losing a lot more flux from your exposure time and efficiency of reading out chunks at a time than you're gaining from having a brighter object. And it's not until you like approach the bright limit of the subarray that you actually get back close to that relative signal to noise. So the thing you want to keep in mind is that when you're at a boundary between the bright limit of 2 subarrays, multi-stripe or otherwise, that's when you're going to be experiencing these significant signal to noise drops and deviations. So for transiting exoplanet hosts, I've kind of plotted this here in this gray histogram. You can see most of them fall in the first 2 stripes we've designed, the broadest stripe sizes, but there are a few, and not a small amount, in these shorter stripe sizes too, and some particularly exciting targets as well. Importantly, the relative signal to noise is never going to be lower than 50% of something at the bright limit for SOS, subscript 256, and the average relative signal to noise is around 75%. Now, that might be okay for most science cases, but there's still some tricks you can play. For one of them is thinking about subscript 96. That still might be preferable for some of your science cases. Yes, it only covers order 1, and you lose that kind of short wavelength coverage from order 2. However, you don't suffer as much from these relative signal to noise losses because you're not chunking up the subarray and you're just being very efficient with your readout and always getting photons when you can. So your best choice is going to be a balance really between your target magnitude and your science goals. And I'll go through a little workflow of this in a minute. The other thing to think about is still considering some level of saturation. So I know some people in the science community do this already. You know, it's worth saturating a little bit in a portion of the detector if I can get a good signal to noise elsewhere in the detector. And that's going to be really important for multi-stripe. You know, if you have something that's just past the bright limit for a given multi-stripe subarray, you really might want to consider using a wider stripe size subarray and dealing with like maybe saturation in one of your stripes to make sure that you get a big increase in signal to noise. You know, we're not talking like a 10% increase. It could be something as high as like 40% increase in signal to noise just by handling some saturation in 2 or 3 pixels or something. But again, you know, this has to be driven by your science goals. How much do you care about saturation affecting your data? What wavelength is the saturation going to exist in? How important that is to you? You would need to weigh all of these for a given proposal. Okay, so here's my workflow for when you're thinking about this. So first question is your target fainter than J equals 8.4? If your answer is yes, you should just be using subscript 256, more than likely. I don't think there's really many compelling reasons to do otherwise. If your answer is no, then your next question should be, is your target fainter than J equals 6.3? If that is yes, then you could still use subscript 96, in which case you need to ask, is, you know, 0.6 to 1.4 microns of order 2 coverage really needed? If you aren't really too interested in it, then you can just use subscript 96. That's going to give you better signal to noise than any of the multi-stripe subarrays will give you. If your answer is either yes to that you want that wavelength coverage, or no, that your target is fainter than J equals 6.3, you need to ask yourself if you care about this detector saturation. If you do, then you can play around with the ETC to explore this SNR saturation trade-offs for these multi-stripe subarrays. And if your answer is no, then you want to be using the multi-stripe subarray with the largest stripe size that avoids saturation. That's always going to give you the best signal to noise.